Let's talk about applications that can come up with these rational functions. So one scenario is going to be calculating average cost. So a variable that we're going to use when calculating average cost is the quantity of items that we're looking at. And the idea is that we'll have a function for cost. So we'll have some C of Q that calculates the cost of the items based on the quantity. So cost of items given a certain quantity. So the idea being, like, if we were producing 100 items, this function C of Q would be calculating the total cost of producing those 100 items. So that cost is going to change based on the level of production that we're working with. So the idea is really, on average, how much is it costing to produce each item? So we're going to call this function AC of Q. So for average cost given some quantity. And what we would do is we take that cost function, so we would take C of Q, whatever function that is, and divide it by the quantity of items. So if we were producing 100 items and there was a certain cost associated with that, if we wanted to know the average cost per item, we would take that total cost and divide it up among the 100 items. So let's try this out. Suppose that manufacturing an item has a fixed cost of $4,000, and per item, so this marginal or variable cost, is $20 per item. So our cost function, C of Q, would be coming from that fixed cost of $4,000 plus 20 times Q from that variable cost of $20 per item. So we have a linear function for our cost. Find the average cost per item when 250 items are produced. Then we can check our answer on a calculator. So if we're finding average cost, let's make a general function first. So the average cost given some quantity, we would take that 4,000 plus 20 times Q, and we're dividing it by Q. And we have ways of simplifying that, but let's just leave it in that form. But that way we can see our rational function where we have that 4,000 plus 20Q as a function in the numerator, and then just Q in the denominator is a function as well. So if we want to find the average cost for 250 items, what we're going to do is plug in 250 for Q. So we're taking 4,000 plus 20 times 250 over 250. And if we plug that into a calculator, that'll give 36. So the average cost is $36 per item when 250 items are produced. So let's take a look at this with the graphing calculator. And what I'm going to do is I'm going to graph the average cost function. So average cost was that 4,000 plus 20, and then we're going to use X in the calculator, and then over X. So let's see, I'm going to need to zoom way out here. And yes, there's something happening in the third quadrant, but since this is a word problem, we're just focusing up in the numerator, or sorry, in the first quadrant here. So what we can see is we come from positive infinity, it turns, and then it looks like we're going towards 0 in the long run, or not 0. We would be, our horizontal asymptote would be a positive 20 in this case. So the degree of the numerator and denominator is the same. So let's talk about what all of this means. So Coming from positive infinity really doesn't mean much in this case, because like we're never going to be producing a fraction of an item. But the idea is like if we produced one item, what that would be 4,000 plus, it will cost $4,020 on average to produce that one item, which makes sense. Imagine you have this entire factory of production and you make one thing. So to pay the wages of everyone, to pay the rent on the building, to maintain the machinery, it's really not cost effective to produce just one item. So that's where we get these really extreme values for a small level of production. We're getting things close to infinity or just really massive amounts. But then it levels out. Once it looks like, especially once we hit a level of production at 100 items, it starts to make more sense. Having a certain, let's see, if it's 100, we're at about 60, it looks like. So $60 per item when we're making 100 items. That sounds good. And then we found that 250, we've had a value of 36. And then what I was saying about the horizontal asymptote is if we calculated it, it would be a horizontal asymptote at 20. And what that tells me is that as production gets bigger and bigger and bigger, the more items that we produce, if you're producing on a massive quantity, that cost levels out because the rent's staying the same, you're paying the same number of people. Maybe just the machines are working extra time, if that's what they're doing here. And with that, it levels out at a cost of $20 per item. So it's kind of like that 4,000 fixed cost. It is important, but it becomes small in terms of the scale when you're producing thousands and millions of items. So that's where the horizontal asymptote comes in here. It's this idea of what happens if our quantity just takes off and everything else stays the same. If that 4,000 fixed cost and this $20 per item stays true, no matter the quantity that we're producing, then that's what's going to happen in the long run. Realistically, there's probably a separate function for when we would produce things at that scale, but if we were able to maintain those values, that's what would happen. Okay, so let's kind of bring those ideas to this scenario. So we have Naughty Products, an eBay retailer that resells items purchased from Fiji, has started a new-to-market product. So Naughty is currently selling 2,000 units a month. Let's just highlight that. 2,000 units a month, which has been growing by 100 units a month. The total market for the product is currently 10,000 units, but is growing by 1,000 units a month. So we have our two scenarios here. We have what's happening for this company. So those 2,000 units a month growing by 100 units a month is specific to this company. So let's have X represent the number of months. So for this company Naughty, how they're operating within the market is, let's see, we're working with everything in terms of a scale of per month. So 2,000 units, and then it's changing by 100 units. So we have our fixed amount of units and then the change in units. So we're going to have that fixed amount of 2,000 plus the variable amount of 100, and then it's per month, so times X. So that company Naughty is operating at 2,000 plus 100 times X. And then we have this idea of the total market. So everywhere is operating with this fixed amount of 10,000 units, and it's growing by 1,000 units a month. So what we want to do is compare how this specific company is operating with respect to the total market. So for the total market, we'll have this function of 10,000 plus 1,000x based on that fixed and variable amount. So we have these two linear equations. So determine Naughty's current market share. So like I was saying, is how is this company comparing to the total market? And with that, this market share idea is the idea of a percentage. Like, how much of the total market is this company taking up? How much are they producing? So if you think in terms of like products out there, so like smartphones, we have all these different options. We have Apple, we have Samsung, we have Google, all sorts of different phones. And there's a certain level of demand in the total market. So out of everyone, there's this demand for phones. So what we could do is think about how many units are absolutely needed, and then how is it changing? How are more people getting phones? But then we could take a company like Apple and see, take a company like Apple and see what percentage of the market are they taking up. So this total market for smartphones, and what percent of that market is Apple taking up. So that's what we're doing here, just with this fictional eBay company, and then this total market for whatever they're selling. So to find this current market share, what we're going to do is create a ratio between these two. So we're going to take the calculation for this company Naughty, so this 2000 plus 100x, and then we're going to divide it by that total amount of 10,000 plus 1000x. So that's calculating the current market share, depending on however many months have passed since they collected this information. And with that, we can see what percentage of the market is this company taking up. So this calculation would actually be in terms of any month. So let's go back here. I'm going to change this to describing it as a function m of x. So just figuring out the market share based on how many months have passed. So if we want the current market share, what we're going to do is say that no months have passed. We're using our current time, and they collected all this information right now. So we want to look at m of 0. So I'm taking 2000 plus 100 times 0, which is just 0, over 10,000 plus 1,000 times 0, which is just 0. So I end up with 2,000 out of 10,000. So this is what they're currently selling. So they're currently selling 2,000 units at Naughty, and then the total market is currently selling 10,000 units. So if we remove this idea of how it's going to change in months to come, we just have this 2,000 out of the 10,000, which is a 0.2. So that tells me their current market share is they're taking up 20% of the current market. That's what they're providing. So Naughty's current market share is 20% of the total market, but current market share encompasses that. All right. So market share is this idea of a ratio of what's happening for a specific company out of the total market. And then a current market share would be what's happening right now, which would be time equals 0. Okay, find the horizontal asymptote and interpret it in the context of the scenario. So this is a case where the degree of the numerator is the same as the degree of the denominator because they're both linear. So when they're the same, we have a horizontal asymptote at y equals, and then it's going to be a ratio of the leading coefficients. So that's going to come from the 100 in the numerator, from that 100 times x, and in the denominator it was 1000 times x. So we're seeing 100 over 1000, which is 0.1. Again, what we're kind of thinking of here is in terms of percentages. So let's think of this as 10%. So this is what's happening as x goes off to, and we're just focusing on positive infinity here, because again, it's a real world scenario. So x approaching infinity is the same idea as time just passing, in the long run of time passing. So in the long run of time passing, if nothing else changes, we expect the market share to approach 10%. So as time passes, Nadi's market share approaches 10%. So what this means, because we just saw their current market share is 20%, so what's going to cause it to go down? Well, they have a growth rate of 100 units per month, and what we saw is the total market is going to be growing 1,000 units per month. So this company, if they're operating on that scale, they're not going to be able to keep up with how the total market is increasing, that total market demand for this item. So that's where, in the long run, if these rates of change hold steady, this is how their market share is going to end up being. They're going to level out at this market share of 10% because that's all they can kind of keep up with. At the beginning of this, they're a big portion of the market. They're making up 20% of that market. But in the long run of things, they can expect to hold 10% of that total market.